Thank you all very much for your time, your patience, and your keen attention this morning. I sincerely hope that this presentation has successfully shed light on exactly how deeply abstract functional analysis can be weaponized to successfully solve some of the most frustrating, computationally difficult challenges in modern electromagnetic physical design. We are incredibly excited about the future applications of this framework in the broader medical device industry. At this time, I would be absolutely delighted to take any questions you might have, or to hear your thoughts and comments regarding the specific algorithmic implementations, the underlying theory, or the physical neuromodulation applications. Thank you once again. To guide you through this presentation, we will follow this route. First, we will establish the mathematical foundations and matrix modeling that transform our physical problem. Second, we will analyze how this reduces to a standard eigenvalue problem via the D-matrix, evaluating the traditional QR approach. Third, we will introduce the paradigm shift toward Krylov subspaces. Fourth, we will address a critical computational bottleneck, numerical collapse due to underflow, and how our SVD formulation resolves it. Finally, we will present the experimental validation and concluding remarks. Let's begin with the core underlying theory. In the rigorous study of Banach spaces, mathematicians are often deeply interested in the norm of a continuous linear operator. This operator norm essentially represents the maximum Churchian stretching, or amplification, that an operator can apply to any given unit vector within that space. We formally define a Arshauter's support vector Schur as that specific, unique normalized vector where this absolute maximum stretching is physically achieved. Geometrically, if you imagine a perfectly round unit sphere being deformed and transformed by a linear operator into a complex ellipsoid, the support vectors represent the specific directions that reach the furthest boundary of that resulting shape. This concept is incredibly fundamental because it allows us to mathematically identify the principal, most dominant modes of interaction and energy transfer within any given linear system. We can take this foundational concept and expand it significantly into the realm of generalized support vectors. Instead of looking at a single, isolated operator, we now consider an entire sequence or family of matrices acting simultaneously. The immense mathematical challenge here is to find a single unit vector that maximizes the combined quadratic form across this entire diverse set of operators. From a purely computational standpoint, this translates to a highly complex maximization problem over a joint multidimensional space. In practical engineering terms, this theoretical expansion is exactly what allows us to optimize physical systems that must strictly satisfy multiple competing criteria simultaneously, such as a medical magnetic coil that needs to perform with exceptional precision across different spatial target regions or varying frequency ranges at the same time. Moving forward, there is a truly fascinating and deeply useful mathematical link between these support vectors and Tikhonov regularization. In many complex, ill-posed inverse problems, where data is noisy or solutions are highly sensitive, we traditionally use Tikhonov regularization to find a stable, meaningful solution. We do this by carefully balancing the data fit against the penalization norm of the solution itself using a regularization parameter. Mathematically, our group was able to rigorously prove that for a very specific, carefully tuned choice of target vectors and scaling parameters, the act of finding the support vector is numerically identical to minimizing a Tikhonov functional. This equivalence is incredibly powerful because it unlocks the ability to apply decades of established optimization theory to our new search for optimal supporting vectors in geometric spaces. Coil optimization. So, why does all this abstract mathematics matter for physical electromagnetic design? Consider the highly complex design process of a transcranial magnetic stimulation coil used in modern neurology. We constantly face two aggressively competing physical objectives. First, we want to maximize the therapeutic magnetic field within a very specific brain region of interest. This is modeled mathematically by our matrix A. Simultaneously, we must minimize strict physical constraints like coil inductance, ohmic resistance, thermal heating, and overall energy consumption, which are all captured by matrix B. This harsh physical reality forces us to seek the extreme operational values of a coupled system where matrix A is symmetric and matrix B is strictly positive, definite. The mathematical support vector of this precise interaction fundamentally defines the absolute most efficient current distribution possible for the physical coil. To computationally solve this coupled physical dilemma, we rely on the generalized Rayleigh quotient. All of our physical constraints, material properties, and target electromagnetic fields are captured within a mathematical ratio that we desperately need to maximize. However, computationally speaking, working simultaneously with two massive dense matrices, A and B, is extraordinarily difficult and memory-intensive. Fortunately, because our constraint matrix B represents physical energy and is therefore strictly positive definite, we can safely apply a Cholesky decomposition. This technique allows us to break matrix B down into a much simpler, lower triangular matrix C and its transpose. This critical decomposition is our first major step toward computational simplification, allowing us to eventually unify the dual problem into a single operator and entirely avoid the highly expensive, unstable calculation of a matrix denominator. By cleverly substituting our variables using the Cholesky factors we just found, we completely transform the generalized two-matrix problem into a standard eigenvalue problem involving a newly constructed structural matrix, which we call D. This critical matrix D is built by applying the inverse of our Cholesky factor to both sides of our original field matrix A. The incredibly complex problem of electromagnetic physical design is now elegantly reduced to merely finding the single dominant eigenvalue and its corresponding eigenvector of this matrix D. While this looks exceptionally neat and simple on a whiteboard, the sheer staggering size of matrix D in modern engineering is a nightmare. In a high-resolution 3D model, we might have hundreds of thousands of individual mesh elements, making the direct explicit calculation of D a nearly impossible challenge for traditional computing architectures. Traditionally, when faced with standard eigenvalue problems, the QR algorithm has been the undisputed gold standard in numerical linear algebra, and it has earned this reputation for several very good reasons. First, it beautifully inherits and preserves the underlying symmetry of the original physical problem, which structurally ensures that our resulting eigenvalues are pure real numbers, preventing the physical model from generating impossible complex noise. Second, it is highly numerically stable because it relies entirely on orthogonal rotations, like Householder reflections, which do not amplify rounding errors. Furthermore, once we strategically pre-optimize the dense matrix into a tridiagonal form, the computational cost per iteration drops significantly. Most impressively, the QR algorithm offers a cubic rate of convergence, meaning it can hone in on the true eigenvalues with breathtaking precision in remarkably few iterative steps. However, despite its impressive mathematical pedigree, the QR algorithm completely fails us when applied to large-scale, high-resolution engineering. The fundamental issue is that the initial transformation required to prepare the full matrix carries an unbearable computational cost of O of n cubed. For modern boundary element method, meshes with millions of degrees of freedom. This translates to years of computing time. More devastatingly, the QR process aggressively destroys the natural sparsity of our physical data. We lose all the beautiful zeros in our physical interaction matrices, causing random access memory requirements to violently explode beyond the capacity of even high-end workstations. Additionally, QR stubbornly computes the entire complete spectrum of eigenvalues, but in our support vector analysis, we only physically care about the absolute maximum extremum, meaning 99% of the computational power and time is completely wasted. This severe computational bottleneck leads us directly to our necessary paradigm shift, the adoption of Krylov subspaces. Instead of foolishly trying to factor or transform the entire massive matrix at once, we iteratively build a much smaller mathematical subspace based purely on repeated matrix vector multiplications. This unique subspace is formed by taking an initial starting vector and repeatedly applying powers of the matrix D to it. By doing this, the subspace naturally captures and isolates the most dominant, high-energy directions of the operator's action. This brilliant technique allows us to essentially project a massive, computationally impossible, n-dimensional problem down into a highly manageable, much smaller k-dimensional space. We are no longer brute-forcing the whole system. Instead, we are surgically extracting only its most dominant, physically relevant features. To actually construct this powerful Krylov subspace in practice, we rely on the renowned Arnoldi process. This highly elegant algorithm involves a strict sequence of 3 iterative steps. First, we perform a matrix vector multiplication, applying our system to the most recently generated vector. Second, we must meticulously orthogonalize this new result against all previously generated basis vectors, usually via a modified Gram-Schmidt procedure, to absolutely guarantee that we maintain strict linear independence and prevent the algorithm from collapsing onto a single vector. Finally, we normalize the resulting vector. By repeating this process, we build a perfectly orthonormal basis that structurally forms a small upper Hessenberg matrix, denoted as H. We then perform a Ritz projection onto this vastly smaller matrix, allowing us to easily extract the dominant eigenvalues of our original massive system using only a microscopic fraction of the required computational effort. Now, a highly critical technical innovation in our specific approach is the clever use of chain systems to ruthlessly preserve matrix sparsity. As I mentioned earlier, explicitly calculating and storing that dense structural matrix D would instantly crash the RAM of almost any standard engineering workstation. Instead, we perform the required matrix vector multiplication for the Arnoldi process in 3 distinct, highly efficient sequential steps. First, we quickly solve a sparse triangular system for C transpose using backward substitution. Second, we multiply that result by our highly sparse physical matrix A. Finally, we solve another sparse triangular system for C using forward substitution. This mathematical bypass trick allows us to perfectly simulate the exact effect of the massive dense matrix D without ever having to actually build or store it in memory, spectacularly reducing our computational complexity from an impossible O of n cubed down to a highly manageable linear scale. Having solved the memory and speed issues, we must immediately address a silent, hidden danger that ruins many numerical simulations: underflow collapse. When we work with highly detailed boundary element method meshes, the spatial distances are so tiny that our raw interaction coefficients are incredibly small, often hovering around 10 to the power of -9. In traditional algorithmic formulations that require squaring the matrix or computing cross-covariances, these tiny physical values become 10 to the power of -18. The critical problem is that this number falls dangerously below the machine epsilon threshold of standard IEEE 754 double precision floating point arithmetic. When this catastrophic underflow occurs, the delicate structural information of the physical mesh is permanently lost, instantly replaced by arbitrary, random rounding noise, which inevitably leads to completely incorrect, physically impossible coil designs. Our definitive solution to completely bypass this underflow catastrophe is to embed singular value decomposition principles directly within the iterative Krylov framework. Instead of squaring the system, we construct and utilize the Golub-Kahan bidiagonalization or block symmetric matrix. By doing this, we can iteratively extract the required singular vectors directly from the original data without ever once having to explicitly form the dangerous cross-covariance matrix. This brilliant algebraic maneuver keeps all of our internal arithmetic completely linear rather than quadratic. Since we are no longer squaring those incredibly tiny physical coefficients, they safely remain at 10 to the power of -9, which is comfortably and securely well above the fatal underflow limit of our computer processors. This strict mathematical hygiene thoroughly ensures that the delicate, complex topology of our raw 3D data remains pristine, guaranteeing that our final electromagnetic design is numerically valid and physically realizable. If we take a step back to theoretically compare these two computational paradigms side by side, the absolute superiority of the Krylov SVD approach becomes undeniably clear. While the classic QR algorithm suffers from an entirely infeasible O of n-cubed complexity that cripples large simulations, the Krylov method scales with remarkable grace, maintaining O of k times n squared operations where k is very small. Our RAM memory consumption is drastically orders of magnitude lower because we strictly only store a few basis vectors rather than maintaining a fully populated dense matrix in memory. Furthermore, we achieve significantly higher relevant accuracy by focusing our computational budget exclusively on the dominant extremes of the spectrum that actually dictate the physical design, completely avoiding highly expensive and fundamentally unnecessary dense matrix inversions by cleverly relying on simple, ultra-fast, sparse, triangular solvers. Importantly, all of these highly promising theoretical benefits are strongly confirmed by our rigorous experimental benchmarking results. If you direct your attention to the plot on this slide, you can clearly observe the raw computation time plotted against the total number of physical mesh elements in the simulation. The orange dashed line tracks the traditional QR algorithm. As you can see, the required time grows violently and exponentially until the algorithm simply becomes unusable for anything beyond a basic toy model. In stark contrast, the solid blue line represents our proposed Krylov-based SVD approach. Notice how it remains beautifully, predictably linear, even as we aggressively scale the physical model up to hundreds of thousands of discrete elements. This profound, real-world scalability is precisely what finally makes the high-resolution design of modern quiet TMS coils and highly complex MRI gradient systems practically possible on standard, accessible, high-performance computing clusters. In conclusion, we have thoroughly demonstrated today that support vector analysis provides an exceptionally rigorous, structurally sound, mathematical bridge connecting pure Banach space geometry to highly applied engineering optimization. We have clearly shown that traditional eigenvalue methods like the QR algorithm completely collapse under the crushing memory weight of modern high-resolution physical meshes, and furthermore, they suffer fatally from catastrophic numerical underflow. By fundamentally shifting our computational paradigm toward iterative Krylov subspaces and carefully employing linear SVD algebraic formulations, we can successfully maintain absolute numerical robustness. This modern approach seamlessly achieves the massive scalability absolutely required for contemporary cutting-edge engineering problems. Ultimately, this pure mathematical framework empowers us to design truly optimal, hyper-efficient electromagnetic systems with unprecedented levels of physical precision, safety, and energy efficiency. For those of you who are interested in delving deeper into the rigorous foundational mathematics and the specific algorithmic proofs behind the concepts presented today, I highly recommend reviewing our research group's recent published work. Specifically, our foundational paper in the Annals of Functional Analysis thoroughly establishes the pure mathematical theorems regarding supporting vectors of continuous linear operators. Furthermore, our subsequent applied publication in Engineering Analysis with Boundary Elements details the specific, step-by-step computational implementations of the inverse boundary element methods and the underflow prevention techniques that we have extensively discussed throughout this morning's session. Thank you all very much for your time, your patience, and your keen attention this morning. I sincerely hope that this presentation has successfully shed light on exactly how deeply abstract functional analysis can be weaponized to successfully solve some of the most frustrating, computationally difficult challenges in modern electromagnetic physical design. We are incredibly excited about the future applications of this framework in the broader medical device industry. At this time, I would be absolutely delighted to take any questions you might have, or to hear your thoughts and comments regarding the specific algorithmic implementations, the underlying theory, or the physical neuromodulation applications. Thank you once again.